Okay, everyone, welcome back to another video in the equations of motion. In this case, doing them for the normal tangential problems. So we have here a block resting at a distance of 2 meters from the center of the platform. And we're given that if the coefficient of static friction between the speed and the block, it's mu s equals to 0.3. They're asking us to determine the maximum speed which the block can attain before it begins to slip. Assume the angular motion of the disk, it's slowly increasing. So basically what we have here, it is a, what's it called? We have a rotating block, and as this block rotates, this block, or as this disk rotates, this block is also rotating along with it, right? But it is only held down by friction. Once the forces are too much, that they will cause this block to slip. This block, of course, will slide down and fall off the disk. So they're asking us to find what is that velocity that the block can attain just before the friction is overcome and it flies out. So let's write down the given. So we have the radius of curvature given here as 2 meters. We have the coefficient of static friction as 0.3. And we know that this one starts from rest. So velocity at the beginning is 0 meters per second. And we're looking for then that final velocity. So notice we have final velocity, we have initial velocity, so more than likely we need to figure out an equation to find our acceleration some way to do this. So for this we gotta do our free body diagram. So in this case, our free body diagram, I'll do 2 free body diagrams actually. One of them will be the top view, as I'm seeing from the top, all right, and the other one will be the side view. So if I see this block from the top, right, imagine it, we're looking at it from this point of view, right, like this. So the top, this is our eye, we're seeing the block from the top. So you see the block from the top, you of course only see a square, and we will have here our directions. So to the right, we will have the tangential direction, right? In this case, the tangential, notice it's tangent to the disk. And then we have our normal direction, towards the inside of the circle. So those are normal and tangential directions. Notice that is as if we look at from the top. So looking at from the top, what are the only forces that we see from this perspective? So what can happen is that the block, it is rotating with the whole disk. But at least in this perspective from the top, we do not see the wave, we do not see the normal force. All we see is, the force of friction that might be acting on the block. So if the block wants to slide outwards, right, as this rotates, the block will want to slide outwards. So if the block wants to slide outwards, then the force of friction has to act inwards. So in that case, the only force that I have here going inwards is the force of friction. So that is my free body diagram from the top view. Now let's do it from this front view or the side view. So same block that we have here, but in this case we're going to be doing we can call it, let's say, the front view. So from the front. So this will be, if you're looking at it from the front, will be through this perspective right here from the front. So in this case, from the front, we only see the tangential direction. We do not see the normal because that's towards inside, inside the board, inside there. That will be our tangential, or normal direction will be inside into the board. We do not see it. And then let's see what forces we see on the side. And in this case, we of course do see the weight, and we will have the normal force of the block. So with this, we can do our equations of motions to figure out information. All right, so let's see. So let's do summation of forces in the tangential direction first, with, of course, where is it? Or not, this is not tangential direction. Actually, this is our z-axis, right? Or these forces are acting on the z-axis. So let's do our summation of forces in the z-axis, with up being positive. And we have here then that this particular block, it's not accelerating, right? It's not accelerating in this direction, right? It's staying still in the disk, so it's not moving up or down in the z-axis. So we can say that the summation of forces in the z-axis is equals to 0. And then let's see what forces we see in the z-axis. Well, that is the normal force minus the weight of gravity into the gravity, and this is equal to 0. So from here we can then determine that the normal force is equals to mass times gravity for this particular case, where this is equals to some value that, you know, we don't really need to calculate. We were not even given the mass of the block, because you will see here that it is not really that important, as you guys will see. But yeah, but we are saying this from that equation. All right, so let's do the next one. So we'll do summation of forces in the normal direction. And with this case, the normal, as we see it in this free body diagram, normal pointing up. So we'll do like this. And this is equals to mass times acceleration in the normal. Or, since we're really looking for velocity, this is equals to mass times v squared divided by rho. So remembering from here, what is the only force acting in this direction? Well, that is the force of friction. So force of friction, it's equals to mass times velocity squared divided by rho. And we can rewrite the force of friction. Notice, we know from friction that is mu s times the normal force equals to mass times velocity squared over rho. Where we already know that normal force, it's equals to mass times gravity equals to mass times velocity squared divided by rho. We have mass on both sides, so we can cancel the masses. That's why it was not given for this problem. We didn't even need it. And we can have then that mu times gravity is equals to v squared divided by rho. So I'm going to write on this part over here. So mu s times gravity is equals to v squared divided by rho. So we'll obtain here that v squared is equals to mu s times gravity times rho. So after you multiply everything here, so mu squared once again is 0.3, we got gravity, we know rho, those are constant values. We should be getting here that the velocity final for this problem, the velocity that the block can attain before it slips out, it's 2.43 meters per second, right? This is the velocity it obtains. So notice, pretty straightforward, pretty easy problems to do, you know. So we'll continue to do another one for this one that is also pretty straightforward.